fractions for boron 11 in Turkey, 79.7%, and then for boron 10 in Turkey was 20.3%. So now we want to find the American, we want to work through the process to find the American percent abundances. All right. So nothing in this problem is going to change except for the average mass, because that average mass in America is different from the average mass in Turkey. The average mass in America is 10. Let me take this whole thing and copy it. No, never mind. Actually, yes. Let's see if I can pull this off. Because there's no change except for the average mass. The whole setup is the exact same as it would be for the previous problem. Let me get rid of what I don't need. Don't need that because now we're not working with Turkish boron. That's going to stay the same. This number right here is going to be different. So for 11. So for the boron found in the United States, that average mass changes to 10.819 AMU. All right. So same setup. Everything is the same except that number. So we're going to have the same. All of this is going to be the same. Let's see if I can copy that. I know I'm cheating. So none of this changes. It's still 0.0931x plus 10.0129 minus 10.0129x. All of that stays the same. Only difference is that this is now equal to 10.819 AMU. That's it, right? So if we combine the x terms, we're going to get that exact same number, which was what? Anybody? It was 0.99641x plus 10.0129. All right, so now we just need to get the x term by itself. So we're going to subtract that from both sides. Right, what is that number going to be? The 10.819 minus 10.0129. What do we get from that?
0.8061.
Good. 0.8061 equals 0.99641 x. So now we're just going to solve for x. That's going to cancel. This will be 0.99641. And what is x in this? And for United US boron?
0.809.
Good. 0.809. My bad. 809 equals x. Right? So this is the fraction. And I'm going to multiply that by 100 to get the percent. So 80.9% is B11. Because remember, let's go back to the beginning of the problem. It said that boron 11 had a mass of 11.00931, and then that's the term that we made the X term because it was the closest to the average mass, right? So this is the term right here for B11, and then this is the term for
No, thank you.
B10. All right, so B11,
You said
80.9%, and then how do we get to B10 again? If that's X, remember one of them was X, and one
To plug in that value for X in the 1 minus.
exactly. So this is X. The 1 minus X term is going to be for the boron 10 isotope. So 1 minus X would be 1 minus 0.809. What do you get for that?
0.191.
191. So this is the 1 minus X fraction. And then we're going to take that and multiply by 100 to get the percent. So it's 19.1% of the B10 isotope, boron 10. So 80.9% for B11, and then 19.9% for B10. So those percentages are based on the fact that the average mass is different in Turkey. For boron, the average mass is different in the Turkish sample and the sample in the United States. All right. But again, the key to the problem was understanding how to look for the fractions, right? And we said that if you have two species, we're going to make one of the fractions X and the other one 1 minus X, because the fractions have to add together to equal 1, or the percentages have to add together to equal 100. All right. Any questions about that second part of that problem? All right, we're going to do one more. This one is a little bit more complicated, but it's not any more scary than the problem we just did. It just involves a little bit more rigor. So let's look at it. And I put plenty of room down here, so hopefully we will have enough room to work through it. Somebody read that and tell me what we're given and what we need to find. Let me zoom in more just so you can read it. Somebody read that problem for us out loud.
You want me to read the actual problem or what's given?
No, read the problem.
Okay.
Mhm.
Magnesium has 3 naturally occurring isotopes: magnesium 24, magnesium 25, magnesium 26, with atomic masses 23.985042, 24.985, 837, 20, and 25.982593 AMU respectively. If the average atomic mass of magnesium is 24.3050 AMU and 78.99% of all magnesium is magnesium 24, what are the abundances of magnesium 25 and magnesium 26?
Yeah, so that's the problem. All of that spinach, and this is what it's really asking right here. What are the abundances of mag 25 and mag 26? What do we know? We know precise atomic masses for each one of the isotopes. And we know the major fraction of one of them, don't we? We know the major fraction for magnesium 24 is 0.7899 or 78.99%. Right? So let's see if we can figure this out. So we have one fraction. So we know the isotope masses. We know the average atomic mass. I'm abbreviating that for breadth for space. And we know one fraction. We know one fraction. All right. So we know that one fraction is 0.7899 for magnesium 24. Is that right? So now this is the key to the problem. Once we get this part, the rest of the problem is academic. If the fraction for magnesium 24 is 0.7899, what's left if everything has to add up to 1? Because we got 3 isotopes.
21.01 is the total amount left.
So the other 2 fractions have to be some derivative of 21.01%. Is that right? Is that what you're saying? So we
Yes.
got 2 fractions left, and we know that what's left is 21.01% because it gave us the fact that 78.99% is magnesium 24. So 25 and 26 have to add together to give me 21.01% of what's left, or 0.2101. Is that right? That's the key to the problem. Now, the question is, because remember before it was x and 1 minus x, this time, the way we solve for the fractions is going to be a little bit different, but not impossible. So the way we solve for the fractions this time, make one x. What's the other one going to be? So x will be 1. All right.
Would the other one be 0.2101 minus x?
Come on here. Come on here. Who was that?
Calvin.
Nice work. Put your Cash App in the chat. I'm buying you lunch today. That was good. You caught that. So the other one is going to be 0.2101 minus x will be the second fraction. That's the key to the problem right there. Once you get that, the setup is cake, because the x term is always going to be with the isotope that's closest to the atomic mass, the actual or the average atomic mass. So we'll know where to put that. And then the other term goes with the third isotope. So let's do that. So at 0.2101 minus x would be the second fraction. Is anybody not catching that? Right? Because the point is it gave us 78%, 78.99% for one of the isotopes out of the 3. So the other 2 isotopes have to add up to 21.01% because that's what's left out of 100%. So then to solve for the other 2 fractions, it's the same setup like the previous problem, but instead of x and 1 minus x, it's x and then the 0.2101 minus x. So those are good. That's how we're going to solve for x using those 2 components, right? So remember our equation: average mass equals the sum of the fraction times the isotope mass. I'm just abbreviating this because of room, just to make sure we have room to work this out, because there's a lot of numbers we got to work through. So the fraction times the isotope mass, it's a sum, right? So we know what the average mass is because the problem gave it to us. It says that the average mass, atomic mass of magnesium is 24.3050. So let's put that in here. 24.3050 equals the first term, we know 0.7899 because we already were given that information, times let's see, magnesium 24 is 23.985042. Right, that's that term. Everybody okay with that? All right. What's the second term? Which one do you want to do, the X or the 0.2101 minus X? You pick. So plus what? Which one of those is closest to the average mass? If the average mass is 24.3050, we got two numbers left. We got 24.9. I'm abbreviating that. It's a lot of sig figs, but 24.98 and then 25.98. Which one is closer to 24?
24.98.
24.9. So we're gonna make that our X term. 24.98. Somebody give me those numbers. 98 what? 5837. Is that right? And this is going to be times X because we don't know what that fraction is. Plus the last term is 25 point what? Hmm, 982593. Is that right? I'll put this in brackets. Is that those are three terms because we got three isotopes. Remember, I think when we talked about this yesterday, I made it a point to say when you see that sum right there, that's going to be however many isotopes you have, that's going to determine how many things you're adding together. And each each bracket is going to have the same two numbers, the fraction plus the isotope mass, plus for isotope 2, fraction plus the mass, or times the mass, plus for isotope 3, the fraction times the mass. Are we following? Anybody not following? And again, your fractions have to add up to 1, or your percentages have to add up to 100. All right. So what do we get for that first number? Let's go and get that out the way. The first number is 7899 times 23.985042. Anybody got that yet?
I got 24.775.
It shouldn't go up. It should go down. Because that's basically 78.99% of 23, which is going to be a smaller number. Did you add it?
Yes, I did. I wrote that down wrong.
Yeah, it should be multiplied together. Let me put a little asterisk in here. So it's that times the other number. That's all right. You can multiply it real quick and give it back.
I got 18.9458.
All right, we'll take that. 18.9458. And that's going to be plus 24 and 24. Let me zoom in. 0.985 837 X. Is that right? Because that's that second term. And then it's going to be, we gotta distribute this one. All right, so we're going to take this number and multiply it by 0.201 and then by X. So I'm going to go ahead and put the X term in since that's, but that's not really any multiplication. We're just gonna put that in. So minus 25.982593x. Is that right? And then that's going to be plus what? What's that 0.201 times 25.9852593? Sorry. What do you get from that? Anybody got that yet?
I got 5.45894.
All right, we'll take it 5.45894. We'll take that. So now we got our terms. We're good. We ready to combine like terms, right? So we can combine these two because those are X terms. And we can combine these two because those are just numerical terms. All right. So let's add those together. We add 18.9458 and 5.45894. Man, it's a lot of numbers. I'm getting tired just reading. We get 24.4047. Did everybody get that in your calculator? And that's going to be minus 0.996756. Yes or no? And all of that's going to be equal to 24.3050. Can't lose sight of that part. We're in the home stretch now. All right. Anybody stuck, lost, falling off the boat? Say something. All right. So now we just need to do what? Get the X term by itself so we can solve for X. So we're going to subtract this from both sides. All right, that's going to get rid of that. Minus 24.4047. Somebody calculate that for me.
Negative 0.0997.
All right, negative 0.0997. Perfect. Now, what do we need to do? Tell me we did. I got all this fit on one page. That's all right. Now, what do we need to do? Don't we need to solve for X now? I'm just going to go ahead and keep the negative signs in so we'll see that they'll cancel. All right, so the negative signs are going to cancel out. This number is going to cancel. And what is X? 0.0997 divided by 0.996756. What do we get?
0.100024.
All right, so 0.10024. All right, so this is the X fraction. Following? And that is going to correspond to magnesium 25, which is right here. right? So that X is for magnesium 25. All right. So that means if we multiply that fraction times 100, it's 10% or 10.02%. Right? Questions? Any questions about that? How are we going to get the other part, the other fraction? How do we do that? If this was the X term, then the other fraction, the magnesium 26 fraction, is going to be right here. So it's going to be what? 0.201 minus what? X. Or minus 0.11024. I'm sorry, 0.10024. What's that? What do we get for that? Is it 0.11007? How many of you got that? And if we multiply that by 100, we're going to get 11.01%, something like that, something in that area. Right, so that's 10%, or 11.01% for the magnesium 26, my bad, 26 isotope, and then 10.02% for the magnesium 25. We can round that down to 10 and 11, and that should give us 100% if we take all those numbers and add them together. 78.99 plus 11.01 plus 10. Do we get 100 from that?
Yeah, I got 100.
All right. So let's recap the strategy for these problems. So for average, mass problems, right? If you have all the terms, so all the terms, meaning you have isotope masses, and fractions. Just apply the equation. Right, so that's again, average atomic mass is the sum of fractions times isotope mass. Right? Anytime if you're missing fractions, So use X and 1 minus X to solve for those fractions if you have a two isotope problem. And make X I'll zoom out in a second. Right. So if you're missing fractions, you'll use X and 1 minus X to solve for those fractions. And if you got a two isotope problem, and you make the X term the isotope that's closest to the average atomic mass. Right. If you have multiple isotopes, then you're going to have to be given at least one of the fractions. So you have more than two isotopes. You got it. You got to have at least one fraction, and then you can solve for the other two. So the difference of the given fraction minus one. Let me not say minus one. Let me just say and one and one. Right. So that's like what we just did. We had 7899 as the fraction. We subtracted that from one. What was left, we solved for those two fractions using X and then that number minus X. All right. Any questions about what we just did? No. You won't use one. That's a good question, Saxton. So you won't use 100 with the fraction because 100 is a whole number. So with the when you are solving for the fractions, you always want to use the decimal, the fractional number. So instead of using 100 minus X, we'll use 1 minus X. I hope that answered your question.
I think so.
Okay. Yeah, we won't use 100 minus X, although it's the same idea because the percentages are based on 100, but the fractions are based on 1, if that makes sense. All right. Let's jump to, we got plenty of time left. Let's jump to another section. And this section is dealing with something totally different because we're going to get into now naming compounds. And let me put a header up here. Right, so under naming, sometimes you'll also see this given using the term nomenclature. Fancy term, same stuff. That just means naming. We're going to learn real quick about molecular formula and empirical formula. So the molecular formula is just the symbols and subscripts. Right? I know that sounds overly simplified, but let me show you what I'm talking about. So this molecule, what atoms are present in that molecule?
Carbon and oxygen.
Excellent. Carbon and oxygen. How many carbons do we have?
Just the one.
Just one. How many oxygens?
2.
2. So we have carbon and oxygen, and we have 2 oxygens. So we're going to list that as a subscript, right? This is the molecular formula. All right, for carbon dioxide. The name of this compound is carbon dioxide. The di here, it's a Greek prefix for 2. The oxide means that there's oxygen present, and the carbon is kind of self-explanatory. So it's carbon dioxide, right? So the molecular formula for that is CO2. All right. Now let's look at this example right here. This compound has a common name. I'm going to give it to you. Actually, I'm going to give you 2 things right here because I can sneak something to you right here. All right, I can sneak in a little piece of information to you right here. Let's go back to when we talked about what were we talking about? I forgot what we were talking about. We were talking about ionic versus covalent bonds. What type of bond is that between those 2 carbons? Anybody remember?
A triple bond.
Excellent. It's a triple bond. In organic chemistry, this is a class of compound that we call alkynes. Right? The YNES on the end gives it away that it is, and that there's a triple bond present. So this is a suffix for triple bonds. Right? So that gives that away. Right? This particular compound, the name of it, even though this is beyond the scope of the class, I think y'all are smart enough, I can give it to you. This is called acetylene. That's the name of this compound. We're not worried about that part though. Let's go back. How many carbons does this compound have?
2.
2 carbons. So we're going to write C2. How many hydrogens?
2.
2. Good. So C2H2 is the molecular formula. Right? Now, the other thing it asks for up here in the top is it asks us also to give the empirical formula. So the empirical formula is like the reduced form of a molecular formula. Let me get my handwriting together. All right, so the empirical formula is like the reduced form of the molecular formula. So you would take those subscripts, if possible, and divide them down to the lowest common denominator. So here, C2H2, we could also write like this, CH, and this would be the C1H1, and this is the empirical formula. Right? Because if you take the 2's and divide them, you're going to get, you can divide both of those numbers by 2 and get 1. So the empirical formula is like the reduced form of a molecular formula. The molecular formula tells you all the atoms that are present and their ratios. The empirical formula just tells you the atoms that are there without knowing how many of each one is actually present. Right? So this is C1H1. It's the reduced form of C2H2. Any questions about that part? All right, let's do the next one. What do we have? Well, this is another good one. I get to sneak you some more information. What kind of bond is that? If there's two bonds between those two atoms together like that.
A double bond.
Double bond, excellent. And this class of compounds, it's an organic compound because it's carbon based. This class of compounds is what we call an alkene. Right, the ene on the end. I'm gonna throw another question in too, because we can also talk about another class of compounds like this. So the ene indicates that there's a double bond present. This compound right here is actually ethylene. Very, this is everywhere. My son, we did a science project once, because this is ethylene itself is a gas. So like if you have an apple, and when apples start to rot or deteriorate, they give off ethylene gas. So we try to trap the gas and polymerize it, right? Yeah, I sent y'all a paper about polymers. So ethylene, you can turn into a polymer. This is the main component of like most of your plastics. It's ethylene. There are some other harder plastics that you can make polymers from other types of monomers, but this is the main monomer for like wrapping, like plastic wraps. I mean, like y'all don't buy CDs anymore, but like back in the day, they used to sell CDs. You had to unwrap it with plastic, or if you have a plastic wrap around, some item you receive in the mail, like if it's shrink wrapped, that's the main component. You got high density polyethylene, like for trash cans and things like that, and then low density polyethylene for like wraps and things like that. So this is ethylene. What is the molecular formula for that? How many carbons does it have?
C2H4.
Come on with it. C2H4. This is the molecular formula. What's the empirical formula? If I took that down to the lowest common denominator, which would be 2 in this case, what would we get?
Carbon 1, hydrogen 2.
Excellent. CH2, right? But the 1 is understood, so we'll just write it like that. Right, and this is the empirical formula. I'm going to abbreviate that. All right. Let's do the last one, and then we're going to stop, because I think we got a few more. We got some naming, but I don't want to start that today. I'm actually going to send you a little video to watch for Monday, and we're going to start that on Monday. So now we know the test will be on Wednesday. Or I may just push it to Friday, because I want to spend some time on this naming to make sure we get it, because there are a lot of different learning objectives tied up in naming. Periodic table groups, charges, polyatomics, all of that. So I want to take time with this. I don't want to rush through it, because the naming part, believe it or not, is a stumbling block. Because when we get further down, you may only just have the formula and know nothing else. And if you have that and you know how to name it, then it makes those problems easier, because you understand what you're working with. So we're going to spend some time on that. As a matter of fact, let's just go ahead and say that the test will be Friday, because I know in the announcement I said Wednesday, but we'll say Friday, next Friday. And the recitation, good question, Asia. It'll be due when we finish this. So we're probably going to finish this on Wednesday. So you can turn it in either Wednesday, or you can turn it in Friday when you take the test. Not today, next Friday. Today is Friday, right?
Yes,
All right.
sir.
Yeah, I'm tripping. Man. All right. So now let's take this We got 4 oxygens. We got a sulfur. This is a good one too. And we got 2 hydrogens. Right. Normally, the way this is written, and I'm saying that because I know exactly what the compound is, we're going to lead with the hydrogens. Right. So this is, how many hydrogens do we have?
2.
So that it's going to be H2. How many sulfurs?
1.
1. So H2S. And then how many oxygens?
4.
4. Good. So H2SO4. Right. Since this is already 1, understood to be 1, there's nothing we can do with this to take it down to its empirical formula, because then we'll have fractions, and we don't have fractions as subscripts. It's always a whole number. So the molecular formula is here. There's no empirical formula because we don't want fractions. Maya, I think that was you that was giving us so much life with these other examples. So put your name in your Cash App in the chat too. Go ahead, Kennedy. Saxton, my bad.
You're fine. So why do we start with hydrogen instead of sulfur?
So there's some conventions, like if it's an acid, which this is the formula for sulfuric acid.
Mm-hmm.
So if it's an acid, you lead with the hydrogen. And I'll walk you through, when we do more of these, I'll walk you through all of that. But that's just a convention that when you're dealing with an acid, you lead with the hydrogens, because it's the hydrogen itself that makes the acid an acid.
All right.
Yeah, great question. Great question. Right. So for organic compounds that are carbon-based, you always lead with carbon. But in this particular case, this is an acid. If it was just S and O, you would lead with the S because it's less electronegative than oxygen. But we haven't talked about electronegativity yet. So we're going to talk about that a little more on Monday. It's another piece that I have to sneak into you because they don't introduce it until like 2 chapters from now. But we can still learn it now. And then when we see it again, we'll have experience with it. All right. All right. So with that said, we're going to stop here. It's Friday. Hopefully you have an enjoyable weekend. You won't have to take an exam today, which is good. But keep studying. If you got the book, keep reading chapter 2. If you're done reading chapter 2, work back through your examples, rework them, even if it's the same numbers, just to get that muscle memory, and Google is your best friend. You want to Google some problems on average atomic mass and things like that, by all means do it. Yeah, it's amazing. All right, have a good weekend. Let me get these Cash Apps so I can get these lunch orders. But thank you for participating, and I appreciate y'all. Just keep pushing. Just keep pushing.
You did record this class, right?
Yeah, it's
I'm
matter
gonna
of
have
fact,
to rewatch it for my own understandings.
it's all good. That's why I record them.